watch it through. I'll go through some explanations and examples, and then I will attach scanned worksheets for you to complete whenever you can over the week to supplement your resources that you already have. This week I'll attach worksheets from Walker Maths and ESA Learning Workbook, just picked to have a variety. You hopefully all have your New Lake book at home, and I will provide you with any page references that I use from that as well. Before going any further, I would like to note that, of course, having not had any lessons with you for quite a long period of time, you're probably wondering about your bivariate internals. Yes, of course, I have marked them, but we haven't had any time together yet since this level 4 announcement. A few of you do have resubmissions to do for me. Again, see any further information that I give when I post this video, and it should all be there for you. I will touch base with those of you that have resubmissions to do so that we can get that sorted this week and done. All right, moving on. This week we need to talk a little bit more about conditional probability and independence, page numbers at the top there. We have talked about both of these concepts in class already, but we brushed over them fairly lightly. Conditional probability is something that you will have been doing at level 2, just not so formally as what we are expected to do in level 3. Independence as a concept was always alluded to, but never fully talked about at level 2, so that might be new for some of you still. Okay, conditional probability first. It's exactly as it states, probability with conditions. Now, when I talk about a sample space, we're looking at the group that we are focusing on. That's what we're referring to there. Keywords to look out for, given that, or if. For example, I might be talking about the weather, or you might be presented with a question about weather in a certain location. We might be looking at the probability of the weather being cloudy. Now, for the purposes of this example, we might say that that probability is 0.4. Now, of course, we need more information than that. So again, in this example, we might have the information that the probability of the weather being cloudy and raining, that probability might be, let's say, 0.32. Now, of course, for any given question, we need a task to actually complete. So for this example, let's say that our task is to figure out what the probability of it being a rainy day, given that it is cloudy. Now, I know that I have used this notation a little bit in class, but if you've forgotten, this vertical line here, it's not an L, it's not a dash or a slash or anything like that. That is the notation for given that. So when I read this probability out, excuse the smudging of the ink, that reads probability of it being a rainy day or raining, given that it's cloudy. Or alternatively, what is the probability of it being a rainy day if it's already cloudy? So that means, again, looking at our definition of conditional probability, that it being cloudy is the condition that must be met. That's what we are restricting our sample space to. So I'm not even considering any possibilities where it's a sunny day and it's not cloudy. Anything like that. It must be cloudy for me to look any further. All right. If we display this in a few different diagrams, let's start with a Venn diagram. We would, of course, have our two situations here. Let's say C for cloudy, R for raining. Of course, this information here, we always work with the most specific information first in a Venn diagram, which of course is our cloudy and raining, and being the wording for intersection. That means that this 0.32 goes in the intersection between our two events, event C for cloudy and event R for raining. Now, because we've got this probability of cloudy only, some of you might be tempted to put that in this remaining space within the cloudy circle. However, that cannot happen because this is the total probability of the weather being cloudy. That means, of course, that the 0.32 needs to be detracted from that. So that leaves us with the probability of it being cloudy only, or cloudy and not raining, is 0.08. Okay, common mistake to make. We have worked on that a little bit in class. Now, that's all we can do at the moment for a Venn diagram. Let's look at another situation or diagram. Tables are probably the easiest for conditional probability, just because they're so familiar to you, having worked on them, hopefully, since year 9. I might draw up my table a little bit like this. Now, overall, we are looking at the weather. I might use the notation C and the complement of C for cloudy over here in the left column, and not cloudy, which is the opposite or the complement. Likewise, rainy or not rainy. Our totals would be on the extreme column and row. Now, of course, going back to our task information, cloudy and raining is the intersection of cloudy and raining. So 0.32 goes in here. We established from what we had to do on the left in our Venn diagram that this 0.4 is the total probability of it being cloudy, meaning it has to go down there. So hopefully that clears it up a little bit as to why we had to do this subtraction to get 0.08. Easy mistake to make. Make sure you spot them and fix them. Okay, final diagram we could do, of course, is a tree diagram. Conditional probability on a tree diagram can sometimes be very simple and can sometimes be quite a challenge, depending on how it's ordered. Of course, the first information that we were given was that something was cloudy. So that was my first stem here, just a natural reaction and how I might lay out my tree diagram. You can see again this notation of complement. Cloudy, not cloudy. Raining, not raining if it's cloudy. Raining, not raining if it's not cloudy. Now note the language that I just used there. Raining if it's cloudy. It's stemming from this branch. But right at the beginning here, I said to look out for that sort of language, using the word if or using the word given. Both could work in that situation. Raining, given that it's already cloudy. So you can see that we are looking at conditional probability using a tree in this case as well. Before we do anything else, we of course need to enter in the values that we have from here. So the probability of it being cloudy along this branch here would be our 0.4. Some of you might be tempted, again to make a common mistake, of writing in your 0.32 here on this branch, thinking cloudy and raining, that's where I'll write it. That's not the case though. We don't actually know that yet. We don't know the probability of it raining, given that we've already established it's cloudy. So, what we actually need to write, probability of it being cloudy, and intersection, I've used that language already, now you're seeing the symbol, cloudy and raining, and that's your 0.32. Remember that if you did this for each of the 4 combinations, all of these values, if we had them, would add up to 1, the sum total of all probabilities in a set. Now we can work with our conditional probability. This is, of course, on your formula sheet. I will get to that in a moment. Looking at your 3 diagrams, work with what is comfortable for you. I said that tables are often the most comfortable, so I'll start with that. If we are looking for the probability of it being a rainy day, given that it's already cloudy, we are quite simply looking for the probability of the cloudy and rainy day happening divided by the probability of it simply being cloudy. Or, as we can see from here, 0.32 divided by 0.4. Let's just make sure we keep this clear so that you don't get mixed up thinking that's a result of our probability tree. This is our conditional probability. Most of you wouldn't have needed that. You would have understood that straight from your table, knowing that the probability of both happening, rainy and cloudy, out of our restricted space. If we look at our Venn diagram, we see the same thing. We want the probability of it raining given that it's cloudy. So already, because we are restricting ourselves to the cloudy total of 0.4, we are only looking within this circle of our Venn diagram. Because we are interested in it being rainy, the only place that satisfies that is in this overlap or intersection. Because we can't spread into this right-hand side, we were restricted to it being cloudy. So we're only left with 0.32 out of the total, which was not 0.08, the total was 0.4, which is exactly what we've just done. Now, of course, that means that if we use our notation from the question, using given that, the probability of it raining given that it's cloudy is exactly what we've just done here. The probability of the intersection of it being rainy and cloudy divided by our restricted total, in this case cloudy. That is the formula for conditional probability. It's how it comes about. Of course, on your formula sheet, we wouldn't necessarily be talking about cloudy and raining, so they use the generic A and B. The probability of A given B, or event A given that event B has already occurred, is equal to the probability of the intersection of those two events A and B divided by the probability of the condition, in this case B. It is always in that order. That is to say that the probability of B given A, if I were to switch these around, would mean I would have to switch these around too. B, which is the second one in this case, is always the denominator. Do not switch these around. Make sure you're careful about that. Now, note that we had a question mark here. What was that probability? Of course, we now understand that actually the probability of it raining, given this branch has already been satisfied, is actually, in this case, the probability of it raining, given that it was cloudy. So, of course, just to finish this off, 0.32 divided by 0.4 is, of course, 0.8, which means that this probability on this branch here is 0.8. There is no place to write them, the conditional probability that is, in your Venn diagram or in your table. There is a place to write it in your tree. Oftentimes you will be able to choose the diagram that suits you best or suits the question best. It is not so often that they start the diagram for you in an exam or dictate what it needs to be. So, it's up to you. Moving on to independence. You can see here my quick note is that independence means that they have no effect on each other. Event A does not affect event B. Let's continue with our example from the left, talking about our cloudy and rainy days. Of course, we've had to state a few assumptions. I'll come back to this keyword here. Let's just add a little bit more detail to our problem though. So I'm going to start by redrawing my tree diagram and giving myself a little bit more room. Of course, I could use my abbreviations again, but I thought I'd spread this out just a little bit more. Now, from the task that we completed previously, we already knew that this here was 0.4, the probability of it being cloudy. I know that as I'm working with the complement, this must be everything that's not 0.4, meaning the probability of it not being cloudy must of course be 0.6. Probabilities add to 1. We also established that this was 0.8 here, the probability of it raining, given that it was cloudy, which must mean that the probability of it being not rainy, given that it's still that cloudy day, is 0.2. The question is what to do with this lower part here, looking at raining or not raining, given that it was not cloudy. Now, if we think about the actual context of the problem, remember that stats is a practical subject, it would make very little sense to assume that this here, the probability of it raining, given that it's not cloudy, was still 0.8, like the set above. Of course, if there are no clouds in the sky, it's quite a low chance that it'll be raining. There are sun showers, of course, where there's very little cloud cover, and generally the day is still considered sunny, not cloudy. But those are quite uncommon. So really, the probability of it being a rainy day, if it's not cloudy, must be quite low. So for the sake of this problem, let's say it's 0.1, which would therefore mean the probability of it not being raining, given that it's not cloudy, would be 0.9. Again, note the language that I've just used there, saying that clearly, if the day is cloudy, there is a higher chance of it being a rainy day, as compared to when it's not cloudy. It's a very little chance that it would be raining at all. The only example really would be sun showers. So clearly, if it's cloudy or not, it does have an effect on whether it's going to be a rainy day or not. So clearly, this situation cannot be independent. There's really no other way around it. Simple context, that is all independence means. We can, of course, go a couple of steps further to actually show this mathematically. Rather than just saying in words that it's not the same if it's cloudy or not, as to whether it's going to be raining or not, we can take that a step further and note the conditional language. Remember, given that, or if. So basically, what I'm saying is that the probability of it being a rainy day, given that it's cloudy, is not going to be equal to the probability of it raining, given that it's not cloudy, or the complement of it being cloudy. Therefore, 3 dots means therefore, both of these would not be equal to the probability of it simply being a rainy day. Now that's something that we perhaps don't quite have yet, the probability of it being a rainy day. Now I know from my probability tree that all possible situations where it is raining would combine to be 0.4 multiplied by 0.8. We multiply along the branches of our tree, which of course is 0.32. We've seen that over here on the left. Second situation, 0.6 multiplied by 0.1, which of course equals 0.06. That means that the sum total of all situations where it's raining would have to be 0.32 added to 0.06, which is 0.38. Now we have all the numbers available to us. The probability of it raining given that it's cloudy was 0.8, which is not equal to the probability of it raining given that it was not cloudy, this one here, which is 0.1. And finally, what we've just calculated, the probability of it simply being raining, .38. The context makes sense, we're just adding maths to it. From this, we come up with a definition for independence. Independence will be in place, it will occur if this is satisfied. If we have the probability of A given B, again now I'm using my general notation, if the probability of A given that B has occurred is equal to the probability of A, then you will have independence. Of course, I could write that round the other way. Probability of A is equal to probability of A given B. The order doesn't matter in an equation. We also know from our conditional probability that this means, well, because the probability of A is also equal to, using this idea, what we've seen here, the intersection of A and B, probability of B. Now, in case you got a little bit stuck just there, I have substituted. That is to say, I've noted my statement here that independence will occur from what we've done here if the probability of A given that B occurs is the total probability of A. If these things were equal, we would be fine. They're not, which is why they're not independent. So the converse is true, that if this equation is satisfied, if these are equal, we have independence. Now, I've noted that I've used my conditional probability here, which we had over on the left here at the bottom of the page. So all I've done here in this next step is replace my conditional probability with what it is equal to. And that has been substituted in here to replace this. So now I can say the probability of A is equal to the probability of A intersected with B, or divided by the probability of B. Now, if we rearrange this, we get something that is a little bit easier to work with. Probability of A still on my left-hand side, but now I'm multiplying out my probability of B. That leaves me on the right-hand side with the intersection of A and B. This is what we can use to state whether something is independent or not. Granted, in a slightly more difficult problem, we may need to use this as well. We may need to use our conditional probability formula. But in the more simple achieved and merit questions, we can get away with just using this simple rearrangement. If you have the probability of A and B, or cloudy and raining total, multiply them together. If that is the same as your intersection, then the equation is satisfied and they are independent. So just to wrap this up, let's check that we can actually do this. So the probability of cloudy multiplied by the probability of raining. These are my events A and B as per the general formula. Now, from our previous calculations, probability of it being cloudy was of course our 0.4, nice and simple, multiplied by the probability of it being a rainy day, which we calculated to be 0.38. Now, if you do that equation, do that multiplication, you'll see that that would equal 0.152. Now, from our Venn diagram, which we could complete from our left-hand side, I'll redo it here on the right for you. Cloudy or raining, 0.08 from our 0.4 minus our 0.32 in the middle here. And we can establish on the right for the first time here that of course we have our total of raining, which is 0.38, but I need to subtract my 0.32 still, otherwise I'd be doubling up, which would equal 0.06. So that just helps us to complete our Venn diagram if we like. In fact, for it to be completed, we would need to have our 0.54 on the outside here to show that all possible probabilities add to 1. Now, we've established that the multiplication of events A and B is 0.152, and we have our intersection of 0.32. Now, of course, 0.152 is not equal to 0.32. Therefore, they are not independent. If you got two numbers here that were exactly the same, this multiplication was the same as your overlap, then they are independent. In an exam question, they will often give you a question that doesn't specifically tell you they are independent or not. This is why I had this warning here to look out for the phrase state any assumptions you had to make. Often they might give you the probability of it being a cloudy day and the probability of it being a rainy day, and they are asking you to calculate this in the middle here. The only thing you're able to do is multiply, but that is assuming that independence is occurring, which in this situation it's clearly not. It wouldn't make any sense in the context. But any time at all, they have told you to state what assumptions you have made, I can almost guarantee that it is independence that you have assumed. They might then go on in a later question to actually remedy what they've said and give you new information about what this overlap is. Makes the problem a little bit more challenging. But in those early questions, if they've told you to state any assumptions, chances are it's independence.